Look up tonight and you'll see one moon pale, familiar, exactly where it is supposed to be. Now imagine a second one sitting right next to it, not a small dot on the horizon, a second full disk hanging in the sky, close enough to see craters on both at once. Tides that don't just rise and fall twice a day, but twist and stack into patterns no coastline on Earth has ever experienced. Nights that are never fully dark, eclipses that happen on a completely different rhythm. An entire evolutionary history of animals, plants, and instincts built around a sky we would not recognize. This isn't science fiction. It is a question serious astrophysicists actually run the numbers on. Not because we expect a second moon to appear, but because understanding why we don't have one tells us something surprisingly deep about the one we already have, and about how fragile the arrangement really is. So let's actually build this world. Let's put a second moon in Earth's sky and follow the consequences all the way through, from the oceans to the length of a day. Before we add a second moon, we need to understand why the one we have is so unusual in the first place. Earth's moon is enormous relative to its planet, not in absolute size and proportion. It is roughly a quarter the diameter of Earth itself, which makes it the largest moon relative to its host planet in the entire solar system, aside from Pluto and its moon Charon. And Pluto isn't even classified as a full planet anymore. Every other moon in the solar system, including the giant moons of Jupiter and Saturn, is a tiny fraction of the size of the planet it orbits. Earth's moon breaks the pattern entirely. The leading explanation is a violent one. Roughly 7 billion years ago, a Mars-Dan-sized object, sometimes called Theia, is thought to have slammed into the early Earth. The collision was so catastrophic it partially melted both bodies, flinging a ring of molten debris into orbit. That debris eventually clumped together, cooled, and became the moon we see today. One collision, one moon. A cosmic accident that just happened to leave behind something enormous, which raises the obvious question this entire video hinges on. What if that accident had gone slightly differently? Jan here is the first fork in the road. For Earth to end up with two moons instead of one, the physics has to work in one of a few specific ways. Option 1, the same giant impact that created our moon could, under different debris conditions, have produced two smaller bodies instead of one large one, if the ejected material had clumped into two separate masses rather than merging into a single moon. Option 2, Earth could have later captured a second object entirely, a passing asteroid or a smaller planetary fragment pulled into orbit by Earth's gravity, the way some scientists believe Mars captured its two small moons, Phobos and Deimos. Option 3, and the most fragile of all, a second moon could form far later from later debris, sharing an orbit with the first moon at a stable gravitational point. Each path is possible in principle. Each one is also wildly improbable, which is exactly why we only got one. But let's say it happened anyway. Let's say Earth ended up somehow with two moons in stable orbits. The very first thing to break wouldn't be dramatic. It would be underwater and enormous. Jan tides are the most obvious place to start because tides are really just gravity made visible. The moon pulls on Earth's oceans, and Earth's rotation drags that bulge of water around the planet, creating the roughly twice daily rhythm of high and low tide most coastal regions experience. Now add a second moon, and the ocean stops following one instruction and starts trying to follow two at once. If the second moon orbits at a different distance and a different speed, its gravitational pull would create its own separate tidal bulge, one that doesn't line up with the first. Sometimes the two pulls would reinforce each other, creating tides dramatically higher than anything we currently experience. Sometimes they'd partially cancel out, creating strange, muted, almost flat tidal periods in between. The predictable rhythm coastal ecosystems, fishing patterns, and entire food chains rely on would become far more chaotic and far harder to predict. Coral reefs, tidal marshes, and intertidal species that depend on a stable, repeating pattern of exposure and submersion would face constant disruption. Some might adapt, many wouldn't. There is a second, slower effect hiding inside all that tidal chaos too, one that doesn't show up for millennia but never stops working. The length of the day itself. Right now, the moon is very slowly breaking Earth's rotation. Tidal friction between Earth and the moon acts like a gentle drag, which is why our days are lengthening by roughly 2 milliseconds every century, and why the dinosaurs likely lived through noticeably shorter days than we do. Two moons pulling on Earth's rotation at once would mean two separate sources of tidal drag. And depending on their distance and orbital direction, that drag could compound, slowing Earth's spin dramatically faster than it does today. Push that process forward long enough, and you get days stretching out far more quickly across geological time. Reshuffling everything from storm patterns to the length of a single day, any calendar on this alternate Earth would even be built around. And that is just the water. The real damage might be happening somewhere far less visible, deep inside the planet itself. Earth's axial tilt, currently sitting at a fairly stable degrees, is the reason we have seasons that tilt isn't naturally stable on its own. Left alone, gravitational nudges from other planets would cause Earth's tilt to wobble chaotically over long timescales. The way Mars's tilt is believed to have swung wildly over its history because it lacks a large stabilizing moon. Our single moon acts like a gyroscope, its gravity locking Earth's tilt into a narrow, predictable range and keeping our seasons relatively consistent for hundreds of millions of years. Add a second moon into the mix, and you add a second competing gravitational influence pulling on that same tilt. Depending on the second moon's mass, distance, and orbital angle, it could either reinforce the stabilizing effect or actively work against it, introducing a wobble that our current single-Jan moon system simply doesn't have to deal with. A more chaotic tilt means a more chaotic climate. Ice ages arriving on unpredictable schedules, regions swinging between extreme seasons on timelines no farming calendar could ever account for. The very thing that makes Earth's climate survivable long-Jan term, its long-Jan term stability, is something we quietly owe to having exactly one moon, not two competing for the job. Gravity doesn't just tug on oceans either. It tugs on air. Earth's atmosphere already experiences its own subtle atmospheric tides, small rhythmic bulges of air pulled by the sun and moon that influence high and altitude wind patterns and pressure systems in ways meteorologists factor into long-Jan range models. A second moon would introduce a second, competing atmospheric tide, layering an additional rhythmic pulse onto global wind circulation. Jet streams, already sensitive to relatively small shifts in pressure and temperature, could shift into less predictable, more turbulent patterns, making long-Jan range weather forecasting on this alternate Earth a fundamentally harder problem than it already is on ours. But climate is a slow, grinding effect. The sky itself would look completely different, almost immediately. Jan. Let's talk about what the sky would actually look like, because this is where the idea becomes genuinely strange to picture. Right now, the moon appears roughly the same size in our sky as the sun, an almost eerie coincidence that makes total solar eclipses possible at all. A second moon, depending on its size and distance, could appear larger, smaller, brighter, or dimmer than the first. If it orbited closer to Earth, it could appear enormous, dominating the night sky, in a way that would make our current moon look small by comparison. If it orbited farther out, it might appear as a smaller, fainter disk, more like a second permanent bright star that never quite goes away. Either way, nights would rarely be fully dark. With two moons in different phases at different times, there would almost always be at least partial illumination somewhere in the sky, disrupting the deep, moonless nights nocturnal animals and ancient human night vision evolved around. And eclipses, both lunar and solar, would follow a far more complex layered rhythm, sometimes involving both moons interacting with the sun and Earth at once, creating types of eclipses that simply don't exist in our current solar system. Ancient astronomers on this alternate Earth wouldn't have discovered one predictable cycle. They'd have had to untangle two interleaved competing patterns just to make a working calendar at all, which brings up something even stranger. Two moons interacting with each other, not just with Earth, two moons sharing orbits around the same planet, don't just affect Earth, they affect each other. Gravity doesn't ask permission to only pull in one direction. If the two moons orbited at similar distances, their mutual gravitational tug could destabilize both orbits over time, causing one to drift closer to Earth or drift away entirely, or in a worst-case scenario, collide with each other directly. There are stable configurations where this wouldn't happen, Certain special orbital positions called Lagrange points allow smaller objects to sit in a genuinely stable position relative to two larger bodies. Mars's two tiny moons, and the small moons found at Jupiter's and Saturn's Lagrange points, hint that multi-moon stability is possible under the right narrow conditions. But for two moons even remotely close to the size and mass of our current moon, the math gets far less forgiving. Larger moons exert far larger gravitational pulls on each other, making stable, long-term coexistence dramatically harder to achieve. Which means the very fact that we have one large, stable moon instead of two smaller, competing ones might not be an accident of luck at all. It might be closer to the only arrangement gravity was ever going to let survive. That same gravitational squeeze has a name when it happens elsewhere in the solar system: tidal heating. And it does more than disturb orbits. It can melt rock. Jupiter's moon Io is the most volcanically active body in the entire solar system. Not because of heat from its core, but because it is constantly stretched and flexed by the competing gravitational pulls of Jupiter and its neighboring large moons. A second moon tugging on Earth from a different angle than our current one could introduce a similar flexing effect deep in Earth's crust and mantle, adding an extra layer of tidal stress on top of the tectonic forces already driving our earthquakes and volcanoes. Depending on the second moon's mass and orbit, this could mean measurably more volcanic activity, more seismic instability, or in gentler configurations, barely any difference at all geology. It turns out, cares about how many moons are pulling on it too, and it wouldn't stop at the planet's surface. Anything we ever tried to launch off of it would face a very different set of rules. Getting a spacecraft safely past one moon's gravity is already a carefully engineered problem, timed around its exact position and speed. Two moons in two different orbits would mean two separate gravitational fields to route around, doubling the number of trajectory calculations, doubling the risk of an unplanned close pass, and doubling the number of ways a mission could quietly go wrong. Even satellites already in Earth orbit would feel it. A second large body pulling from a different direction introduces extra-orbital perturbations, the kind of small, cumulative nudges that satellite operators already spend enormous effort correcting for with a single moon in the sky. Every rocket launch, every lunar mission, every satellite network on this alternate Earth would be running the math against twice the gravitational complexity we deal with today. And if it hadn't survived, the story of life on Earth might have needed an entirely different opening chapter. This is where it gets genuinely interesting for biology, because tides didn't just shape coastlines. Some researchers propose that the regular rhythm of tidal pools exposed to air and then submerged again on a predictable cycle played a meaningful role in the transition of early life from ocean to land, providing a kind of evolutionary stepping stone environment. A wildly unpredictable tidal system, driven by two competing moons instead of one steady rhythm, could have made that transition far messier, or pushed it toward entirely different evolutionary strategies altogether. Circadian rhythms, the internal clocks nearly all life on Earth runs on, are deeply tied to predictable cycles of light and dark. Many marine species time their reproduction directly to specific lunar phases, a strategy that depends entirely on the moon cycle being consistent and predictable year after year. Corals across entire reef systems can spawn on the very same night, guided by lunar cues refined over millions of years, introduce a second moon with its own separate competing phase cycle, and that precise synchronization becomes far harder to maintain. Species that evolved to trust one clock would suddenly be getting contradictory signals from two. Navigation itself would get harder too, and not just for reef fish. Sea turtle hatchlings famously crawl toward the brighter horizon over the ocean, a cue shaped by moonlight and starlight reflecting off open water, which is exactly why artificial beachfront lighting disorients so many of them today. Dung beetles, one of the few insects known to navigate by the stars, use the soft glow of the Milky Way itself to roll their dung balls in a straight line. A second moon, bright enough to wash out fainter light in the sky, could scramble both of these systems at once, turning a reliable celestial compass into a much noisier, less trustworthy signal. Evolution doesn't stop working under those conditions. It just builds different solutions, potentially very different ones from the biology we actually have today. The version of Earth with two moons might still have oceans, life, even intelligence. It almost certainly wouldn't have us. not in any form we'd recognize. Jan. Let's bring this back to human history specifically, because the cultural impact would have been just as strange as the biological one. Nearly every ancient calendar system humans ever built was based, at least in part, on lunar cycles. The word month itself comes from moon. Religious festivals, agricultural planning, and navigation all depended on one predictable, trackable object moving through one repeating cycle across the sky. That last one, navigation, deserves its own moment. Because for centuries, the moon wasn't just a symbol, it was an instrument. Sailors long before satellite positioning used what is called the lunar distance method, measuring the precise angle between the moon and specific stars to calculate longitude far out at sea, where no landmark existed to check their position against. The entire method depended on the moon behaving as one single well-charted object moving along one predictable path. A second moon would have handed those same sailors a genuinely useful new tool, an additional celestial reference point to triangulate against. But only after generations of astronomers had done the much harder work of untangling two overlapping paths instead of one. A second moon, with its own separate and non-aligned cycle, wouldn't have simplified any of that. It would have handed ancient civilizations a genuinely harder mathematical puzzle, one requiring them to track two independent, overlapping cycles just to build a working calendar at all. Some historians of astronomy argue this might have accelerated certain kinds of mathematical and astronomical thinking, forcing earlier civilizations to develop more sophisticated tools to reconcile two competing cycles. Others argue the opposite, that the sheer unpredictability might have delayed reliable calendar systems by centuries, since no clean, single pattern would have been available to build one around. Either way, mythology would have looked completely different. Nearly every human culture built stories around the moon as a symbol of time, femininity, tides, madness, and death. Two moons, competing, sometimes aligned and sometimes not, might have generated entirely different mythological frameworks, sibling gods, rival deities, or twin forces locked in eternal competition across the sky. The sky itself would have written a different mythology, because the sky itself would have looked and behaved completely differently. So here is the strange, quiet twist buried underneath this entire thought experiment. We started this video imagining what we'd gain with a second moon. A brighter night sky, stranger eclipses, a more dramatic view above our heads. But nearly every serious model of this scenario points the same direction. A second moon wouldn't have been an upgrade. It would have been a destabilizing force, working against nearly everything that makes Earth's current arrangement so quietly, invisibly perfect. Chaotic tides instead of predictable ones. An unstable axial tilt instead of a locked gyroscope steady one. Gravitational competition between two large bodies instead of one clean, stable orbit. Disrupted biological rhythms instead of the reliable cycles life has spent billions of years calibrating itself around. The single moon we have isn't just a nice detail in Earth's story. It might be one of the quiet load-bearing pillars of why any of this worked out at all. A specific, precise result of a specific, precise collision, billion years ago, that happened to leave behind exactly one large moon instead of two smaller competing ones. So the next time you look up and see that one single familiar disk hanging in the sky, don't think of it as ordinary. Think of it as the version of this story that actually got to happen, out of countless others that could have gone very differently, and mostly didn't work out nearly as well. One moon isn't the boring outcome. It might be the rare one.